Well, hello. I'm Dr. David Dobrzykowski. I'm an associate professor of supply chain management here at the Sam M. Walton College of Business at the University of Arkansas, where I also serve as the director of the Masters of Science program in supply chain management. I'm really happy to be with you today to talk about some important issues related to safety stock models in inventory policy. So specifically, you're probably familiar with the old sawtooth diagrams or economic order quantity models that essentially say as you deplete inventory, you're going to calculate a reorder point, which is just the demand for your product multiplied by the lead time. That'll give you the reorder point, at which time you'll place a new order for queue, and this process will just continue on and on. And that's wonderful, right? When you have a strong sense for committed demand and guaranteed lead time from your suppliers. Environments, let's say, where you're doing contract manufacturing and you know that you have to build 200 million units, by the next 2 years. Those are wonderful types of models in those environments. But as you start to move, further downstream, in the retail, tiers of the supply chain, or even working in logistics and distribution, you start to see that demand in many contexts is not fixed. It is not known, right? We can take steps to calculate, say, the average demand, and even to the extent possible, the average lead time from suppliers. For example, suppliers aren't always, perfectly on time, right? They may say that the lead time for this product is 5 days or 1 week, but the truth is it may come in 3 days 1 week and 7 days the next week, and the average may be 5. So as soon as you start to introduce uncertainty or variance, right, in our demand and our lead time, it necessitates introducing safety stock into our inventory models in order to deliver on our customers' needs for customer service. And again, in supply chain, what customer service levels mean to us is that we're filling orders. So we set service levels in a very quantitative way. We say that we'll have 90% or 95% or 98% customer service levels. And those are tied to the likelihood of filling customers' orders. So while it's important to be nice and create great experiences for customers, from our perspective, customer service from an inventory viewpoint can be very specific and very quantitative in nature. So I wanted to talk to you today about an example that I have that illustrates just the value of what variance and uncertainty can bring in a supply chain. When I say value, what I really mean is cost, right? What is the value of not having that kind of uncertainty? So let's walk through a short example today. Let's say that you have an organization that has daily demand for one-time use medical product held by a distributor that allows for normally distributed data with a mean of 2,500 units and a standard deviation of 500 units. Now that's just a fancy statistical way of saying on average we sell 2,500 units, and if you think about how much variance there is in that average, there's one standard deviation of about 500 units. In other words, this is probably overly detailed for you, but basically 67% of the time we're going to be between 2,000 units, which is 2,500 minus 500, and 3,000 units, which of course would be 2,500 plus 500 units. 67% of the time we're going to fall kind of right in that sweet spot of 2,000 to 3,000 units with an average of 2,500 units. Well, you know that when we're calculating and determining inventory policy, it's very important, of course, to take into account our safety stock holding costs. When we do that here with the word problem, it tells us that the holding cost for our safety stock is going to be $200 per unit per year. So the distributor has a target service level, a customer service level, like we've discussed in the past, of 95%. So we're going to have to develop a model that accounts for that in some way. And it's known that our current carrier that we have under contract has a guaranteed lead time for delivery from the manufacturer of 7 days, so our L equals 7. This is fantastic. So when you talk about efficient supply chains, particularly supply chains like with functional products, and we talk about the importance of on-time, in full deliveries, right? And we start to talk about service level agreements or SLAs where we have stiff penalties for late or early deliveries. This is that type of an environment where a supplier is guaranteeing us 7 days, no variance. So What happens in our scenario here is that another carrier comes along. So suppose that the distributor is currently evaluating a proposal to switch to a new carrier who's aggressively looking for business in our region. They're out buying business. They're trying to penetrate our region and take business from an incumbent carrier. So if we switch from our current carrier to this new carrier, the new carrier is promising us a potential savings of $250,000, 250 grand. Wow, that sounds awesome, right? But not so fast. Let's find out. But the new carrier's shipping lead time, in other words, what we'll call L prime, which is the estimated lead time, it's random, and that sounds terrible in practical terms, but all that means mathematically is that it's not fixed and it follows a normal distribution. So it's random and it has an expected lead time of 7 days. But because it's not guaranteed, there is some variance, and that variance is measured by a standard deviation of 1 day. Well, how bad can 1 day be, right? It's 1 day. How much of an impact can it have? Let's find out. So, should we change to this new carrier, or should we keep our incumbent carrier? All right, so this slide's going to be a little bit scary. Hang in there with me. It's a little bit Greek, a little bit mathematical, but it's not that bad. I can help you translate this, right? So let's say that with the current carrier, right, and we have our 7-day guaranteed lead time. If we go about calculating the cost of this inventory policy, it's going to be as straightforward as follows, right? We're going to say our mu here, which is really just our reorder point. Many times we call this our rope or our reorder point, is a function of lambda times L, where lambda is just a fancy way of saying our demand. So it's demand times lead time, so D times L. So when we take, when we follow this through, our average demand is the 2,500 units. We multiply by the 7 days of guaranteed lead time, and we end up with a reorder point of 17,500 units. So what that means is that as that sawtooth diagram comes down, we're going to hit that reorder point of 17,500 units. We'll place an order, and we'll continue to deplete the inventory. And if we're doing this right, when we run out, when we hit 0, we'll get that next queue, and we'll continue that process. So that's a reorder point, but that doesn't account for any safety stock, right? We did say that we have an average demand, right? That average demand is 2,500 units, and it has a standard deviation of 500 units, basically plus or minus 500 units to get to capturing about 67% of those points. So we need to account for that variance when we set that reorder point that I was talking about. So to account for that variance, what we're going to do is calculate what we call the standard deviation of demand during lead time. To get that, we're just going to take the standard deviation, multiply it by the square root of the lead time. In other words, we're accounting for the variance in the demand that is taking place during the lead time. So that would be 500, the standard deviation of demand, multiplied by the square root of 7, our lead time. And that gives us what we call a safety stock factor of 1,323 units. All right. So we're all set, right? Let's just add it to the 1750 and off we go. Not so fast. Well, why not so fast? In other words, if you go back to the word problem, right, you'll remember that we said that we want to have a customer service level of 95%. That's what they call alpha here, but that's really just saying we want a customer service or a cycle service level of 95%. So how do we figure out how to adjust that safety stock factor, the 1,323, to get it to 95%? Well, I'm glad you asked. For that, ta-da, you use your normal standard distribution table, right? So this is that old z-score table that you may remember, right? That allows us to take that probability of not stocking out, in other words, 95%, and assign a z-score to it that tells us how much we need to adjust up that safety stock factor of the 1333 to achieve that 95%. So let's go to the center of the table here and let's look for 95%. We see that it's going to be right about here, okay? So the way we use the table is to simply come across and say, okay, our z-score column comes down. It's going to be 1.6. I'm going to follow across 1.60, 1.61, 1.62, 1.63, 1.64. So it's right in between 1.64 and 1.65. So technically it'd be 1.645. However, for our intents and purposes, 1.65 will be fine. So what we need to do is adjust this safety stock factor of the 1,323 by a value of 1.65. In other words, multiply 1.65 times the 1323. That's going to give us a safety stock factor of 2,183, which means then that when we reorder, we're going to add that 2,183 to the 1,750. In other words, we're going to be at 19,683, and that will be the point at which we hit the reorder point, and that triggers another order to be released. So when we go about calculating the holding cost for this, remember we said that the holding cost for our situation here was $200 per unit per year. You see that in the word problem here, holding cost, $200 per unit per year. So what that means then is that we have to take this 2,183, which is the average inventory that we're going to have in addition to that 17,500, and we have to multiply it by the $200, which tells us that the safety stock value alone for this company is $436,600. Okay, so this is useful in so many ways, right? Already, we're able to have an informed conversation with our managerial colleagues that if they want to have a customer service level of 95%, the value of that is going to be, $437,000. What if they're willing to back off of that and instead of 95%, maybe have 90% customer service level? Well, if you want to have only a 90% customer service level, you can find that value as well. 90% is going to be right about here. About 1.30 is going to get you pretty close, maybe you have to extend the table, 1.3, 1.29, 1.28, somewhere in there. So think about that now. If you take this 1322 and you multiply it by, say, even 1.3 instead of 1.6, now you can start to recalculate your safety stock holding cost and determine what the savings of that decision might be. Conversely, if you want to, upgrade your customer service levels to, say, 98% or 99%, you can quantitatively calculate, of course, what the value of that decision is, and now enter your managerial meetings and have informed discussions about the value of that safety stock. In other words, if we, were to increase this value to 98% over 95%, is it really worth the extra, whatever it would be, $100,000? In other words, would we secure $100,000 more sales to offset that cost? In this case, we're focused on the lead time from the new carrier and thinking about whether or not we should make a change in carriers. So our current situation has a safety stock value, like I said, $436,600. But this new carrier came along and he said, hey, look, I've got some great pricing for you. I'll save you $250,000, $250,000. Matter of fact, I'll even give you the same average lead time, 7 days. Sounds great. But there's variance in this one. In other words, it's not guaranteed, and you have to give me some wiggle room of plus or minus a day. That's going to be my standard deviation is plus or minus 1 day. So let's figure out what is the value or the cost associated with that variation. So here, we're going to say now that our estimated lead time, or L prime, is 7 days, and the standard deviation of that lead time is 1 day. Now when I go to calculate my reorder point, again indicated here by the Greek letter mu, it's going to be equal to lambda, which again is just the demand, multiplied by my estimated lead time, which is the 7 days. So it's the same as you saw above, the 2,500 units times the 7 days it takes to arrive, the lead time. In other words, 17,500 units. But now the calculation for the safety stock factor becomes more complex. Now we have to account for not just variance in demand, because remember that 2,500 number for demand is not fixed. It's an average, so therefore if it's an average, it also has spread in the data. So in addition to taking care of or accounting for that variation, which we did here, we also have to take into account the variation that exists in my lead time, that standard deviation of 1 day. So this leads to a little bit more involved type of calculation, right, which I'll show you down here. So here we're going to calculate the standard deviation for demand during lead time as just the standard deviation for my demand. So that's that 500 units multiplied by the square root of my lead time, 7 days. So you see we're accounting for the lead time and the variation in demand during that lead time. We're going to add to that, of course, then the lambda squared, right, which is just going to be my demand now squared, multiplied by the standard deviation squared of my lead time. So here I'm accounting for my lead time variation. And of course here with my demand, I'm accounting for that variation in demand by taking the square root of the lead time and multiplying it by the standard deviation of the lead time squared. So when I make these calculations, right, I come up with a new value, the 2,828.4 units. Let's call it 2828, right? So we see that the difference by just adding a single day of variance in my lead time for my supplier, all other things held equal, is about, 1,500 units, 1,506 units, 2828 versus 1322. But again, this doesn't take into account, that customer service level that I'm aiming for, that 95%. So this is going to get even worse, right? Because when I take into account that service level requirement that I have of 95%, what that means is I have to take this 2828, multiply it by that z-score that I found in the table earlier, the 1.65. So when I come down here and I take that 2828 times the 1.65, it produces a value of 4,667 units. Okay, so look, now we can see that the difference of 1 day's lead time variance, not even an increase in the lead time, but just in the variance or the consistency of the lead time, takes us from a value of about 2,183 units to needing to have safety stock of 4,667 units. So more than doubles the number of units. When we take that now, actually, of course, 215% increase. So when we take that value now and we multiply it by the holding costs, remember we have $200 per unit per year in holding costs. That 4667 times 200 means that our safety stock holding cost. So this is not the holding cost of our cycle stock. This is not the holding cost related to that just demand by lead time. This is the holding cost solely attributable to safety stock because of the increase of 1 day variance in my lead time. 200 times the 4,667 means that I'm going to need to keep nearly $1 million worth of inventory on hand now just for safety stock, $933,400, which of course is substantially higher, nearly double my safety stock holding cost of the 4660 with the current carrier, where I have guaranteed lead time of 7 days. So when that new carrier is entering my market and says, I'm going to give you that $250,000 break, guess what? Doesn't look like it's worth it, right? Because we've got, actually more than twice as much, increase just in holding costs. So that $250,000, that $250,000, doesn't get it done for me, right? Let alone all the additional managerial issues that I'd have to deal with onboarding a new supplier, developing new interfaces and new relationships and so forth, right? So, in summary, today I wanted to illustrate some of the key ideas around safety stock models, reorder point models with safety stock, and also talk to you a little bit about the value of variation and how important it is to take a very quantitative, data-driven approach to decision-making around, variation. In this case, it may have saved you from entering into a new contract that you may regret down the road. So I hope you enjoyed our talk today. I hope it was useful for you. I can hardly wait to see you again next time. And woo pig suey!